sake of completeness. Yeah, okay. So I often stumble upon the term GAN, Generative Adversarial Networks, and I really didn't have a clue what it is. And also everybody said, if you understood deep learning, feed-forward neural networks, LSTMs, recurrent neural networks, convolutional networks, then that's the next thing to understand. And then I thought, okay, I understand all those other types of networks, because I'm teaching them on Coursera, I have to understand those as well. So it's relatively simple in a, let's say, on a broader perspective. Of course, if you dive into the code, it's not totally everything's clear, but I will just share everything what I understood so far, okay? So first question here is, who doesn't know what the deep feed-forward neural network is? Who doesn't know what a convolutional neural network is? Or maybe other. Who knows what who knows what a recurrent neural network is? A recurrent, okay. Who knows what the LSTM, long short term? Okay, that means, okay, who knows what the deep feed forward neural network is, or how it works? Okay, then I have to do some crash course, because otherwise it doesn't make sense to explain GANs. So I'm taking this from the Coursera course I'm teaching, and this is so linear algebra, vector dot product. You know, who knows what a vector dot product is? Okay. So then the feed-forward neural network, I think I can do really fast. So this is basically.
Got it.
So if it's too fast, take my Coursera course and look it up there. But the thing is, we start with a linear regression model, which is basically a vector dot product between a weight vector and a data vector. And we turn a linear regression model into a binary classifier by applying a squashing function, for example sigmoid, which maps from -infinity to +infinity to a range of -0 to 1. Then you apply a threshold, you get a logistic regression model. You see here the linear regression in the middle, a sigmoid, which is 1/1 plus e to the power of -x. Then you have logistic regression. Then you have the simplest neural network, a perceptron, where you take the input data, multiply it with a weight, sum it up, add a bias, and this part is linear regression. And then you have here a step function, then you get a perceptron. And if you put some other activation function here, you get a neuron. So the basic idea is one neuron can be expressed as a sequential computation of one linear regression model plus an activation function applied. And then the idea of the hidden layer, the reason why you add hidden layers is that you then get a so-called universal function approximator. That's a theorem, so it's proven that you, with a single hidden layer neural network, you can represent any mathematical function. So that's about deep feed-forward neural networks. And then there are the convnets. Those are basically the reason why we have this hype, because they are outperforming humans in the ImageNet competition. So the human baseline is around 6% error, and the convnets then started to have only 3% error. So we use those for image classification, and the reason why we don't classify images like this, where you have basically a function mapping from all the pixels to a class or to a one-hot encoded vector, is that if you just line up all the pixels, you lose the spatial information. Therefore, you use convolution. So that's an example for a 1D convolution, which basically you convolve the red function over the blue, and you get the black one. And you can also do that in 2D. So that's a matrix, which represents a monochrome image, 0 for black, 1 for white, for example. It's 1, 2, 3, 4, 5 by 5 image, pretty boring image. Then you have the convolution matrix. That's a matrix you learned during training, and the convolution matrix is convolving over the original matrix in strides. And here you have the AND operation. So if there's a 1 in the image and a 1 in the convolution matrix, you put a 1 in the result. Afterwards, you do some pooling, you add up all the numbers in this result, and you put that in the result matrix. And you do that for all those, and you apply stride based, so there's a 1 by 1 or 2 by 2 strides. That's the configuration you have. So that's the intuition. You have now, after training, something interesting. Here you have an example of a 4-class classifier, so supervised machine learning, which has been trained with many layers, and after training, the input and the middle layer and the output layer has been sampled for different images, and the activations of the neurons have been visualized. And you see here in the bottom that you don't see any concrete examples of faces and cars, just lines, rectangles and circles, and that they are all the same. And that means independently of what image you are classifying, you are learning the same type of filters. So they are some sort of universal, and they are outperforming all the filters which have been handcrafted by the computer vision guys for years, so they are all out of job. And the other thing is that you learn some internal lower dimensional representation of your data, which you don't have access to, and I will come back to that later, why we are using GANs here. So just for completeness, there's another type of layers in ConfNets, which is a mistake if we believe what Ian Goodfellow is saying. I think Ian Goodfellow is saying that pooling is a mistake. Anyway, pooling means reduce the dimension of your data by preserving the spatial properties. You see here that's max pooling. You take 4 elements of your vector, you take the maximum value and put that into the result. That's a way of reducing dimensionality, preserving spatial properties. So that's a toy example of a ConfNet. You have the so-called feature maps. So if you go back to this example here, those intermediate layers are feature maps. So they are called maps because they are 2D, otherwise you would call them feature vectors. And the idea is during training in different layers you have different feature representations of your data. So you are learning latent features about your data which you can't access so easily. And you have then subsampling. Subsampling is another word for pooling or dimension reduction or 2D dimension reduction in this case. Then you have a fully connected layer at the end, and according to the number of classes you have, the layer has that many output neurons. And the activation function you use at the end is softmax then. That's basically it for ConfNets. Just for sake of completeness, I just introduce LSTMs and autoencoders. That's not necessary for understanding GANs, but I love those two guys. So LSTMs stand for long short-term memory networks. And the idea is you have the universal function approximator theorem, which says that a neural network with a single hidden layer can represent any mathematical function, but the function is stateless, and therefore a feed-forward neural network can't remember any state. If you now add memory to a neuron, so you have here a neuron mapping from xt input to ht because it's the vector we send to the next hidden layer, therefore h. And the activation function, those components you have anyway, but here we have now an additional CT, which is the cell state, so that's memory you have in the neuron, and you control the memory by input, output and forget gates. So if you now see here, you have the input data. The input data now also is sent to the input gate, so the input gate you can think of some sort of a ordinary feed-forward neural network, which learns during training from the data when to open and close the input gate. And it also learns from the current cell state. So the current input plus the current cell state decides how much of the current input is stored into the cell state. For output you have also current input data plus current cell state gives us an idea of how much of the current cell state we want to send to the next hidden layer. And finally, we have the forget gate, which says, based on the current input plus the current cell state, we decide how much of the current cell state we want to retain. Given those properties, this whole neural network becomes Turing complete. Yes?
And just a short question, are all the gates are connected, or? is it possible that all gates are closed?
It's a valve, so it's a discrete, a continuous value. It's between 0 and 1 range. Okay, between totally closed and totally open. So this is Turing complete. The LSTM is Turing complete, so it can learn any, or represent, not learn, represent any type of algorithm. And finally, the next cool guy is the autoencoder. So as of now, I've only introduced supervised machine learning examples. Now, if you now have unlabeled data, you can show the neural network the same data on the left and on the right hand side, and the neural network, since it's a universal function approximator, will learn the identity function and reconstruct your data. If you now, so that's the identity function. If you now add, a bottleneck to this neural network, layer with far less neurons than you have in the input and output layer, then you force the neural network to go through that bottleneck and not to learn any irrelevant or noisy data. And at the same time, so that's for anomaly detection, you can use that for anomaly detection because it has only learned the very most important inherent patterns in your data. And now imagine you have a couple of LSTM layers, you can also learn the most important and inherent latent features of your time series. And whenever some pattern arises which have not been seen before, the neural network will have a higher reconstruction error that we use for anomaly detection. So that's the current state of the art of the anomaly detectors we are using. And then dimension reduction is also pretty cool, because if you now train a neural network once with all your data, and the second time you fix the weights, you don't train it but show the neural networks all the data points once again, and in contrast of reading out X prime, you read out C, you get the dimension reduction, which outperforms PCA, for example. Okay, so that was a fast track intro, and now let's see what we have on GANs. So that's pretty new to me, so but they are quite impressive. So I told you in the conf-nets we have the ability to recognize images, categorize or classify images due to latent feature representations in the neural network, but unfortunately they are hidden to us because we only have the input and the output is basically only a probability, a one-hot encoded or softmax output. So in GANs we do something different. So we have two different types of neural networks. One is called discriminator. You see here, that's by the way not a fake image, that's real, that's our CEO. I met her once in my life. And I asked her for a selfie, of course. So that should give us a probability of 1 because it's a real image. And I never met Arnold Schwarzenegger before. So that should give us a probability of 0. Okay? So this discriminator neural network has to detect false images. Now, where do those false images come from? They come from another neural network, which is some sort of the inverse of a conf-net. So we are not doing downsampling, we are random upsampling and so on. From a random vector, so that's a one-dimensional large latent random vector, and from that we generate images. Initially, of course, we only generate noise. Okay? So the discriminator will have an easy time in finding out which is a real image and which is a fake image. But we see later we have one joint optimization objective between the discriminator and the generator, and eventually the discriminator will get better and better in classifying fakes against real images, and the generator will get better and better in creating images where the discriminator thinks they are real, but they are fake. Okay, so that's the discriminator. It's trained with real images and the label 1, and it's trained with false images and the label 0. And here you have the generator part. Okay, so that means you have here one new model, which is the composition of the generator and the discriminator. So I haven't digged into the math too much, so that's on my list, but that's my understanding until now. Okay. And then what you do, you optimize M over T. So T is your training data. You have a joint optimization objective. That means you will generate the perfect generator and the perfect discriminator at the same time. And the discriminator then you can throw away. And the generator is the one you will use in most of the cases. Okay, questions so far? Additions, who knows it better?
Okay,
Yeah?
one question.
Okay.
What's with the background on the false image with Schwarzenegger? Is that irrelevant? Because the detection of this false image is quite simple because of the background.
Yeah, so that's maybe a bad example because actually the generator won't generate such an image. It will be better because it tries to fool the discriminator and it will create images which are looking like that.
Okay.
We will have a little example for the MNIST dataset later. The applications, there are a lot of toy applications so far, but I believe there are many more. So you can create new, what are those called? Characters, there is a specific name. Anyway, Japanese anime, I will, once the MNIST example is completed training, so it runs for 42 hours, unfortunately, I will create new CryptoKitties. That's mine. So I bought a CryptoKitty, I have to confess, last week. A Generation 0 CryptoKitty. I thought maybe I should invest in one Generation 0 CryptoKitty. So you can do property transfer, I call it property transfer. So you have here a picture and you apply a new pose and it will basically generate an image with a new pose. Of course, by training it with different pictures and poses. Then you can transfer also properties. So I don't know. I don't have to explain it what happened. No, it's pretty impressive in my opinion. Or you can extract objects. That's even more impressive. No, you have pictures of people with clothing, and then the GAN extracts the clothing. So all the right-hand side pictures are generated by the GAN. Or you can sharpen images. So by training it with blurry images and sharp images as the target, it will learn how sharpening images work. That's the cool thing, though, that the latent feature transformations which are now stored in the generator can be used for generating something new. Or here, that's also, usually you go from this to that, where you have an image and then you create a semantic map. But here, with a semantic map and the GAN, you can create the image. So all those information, of course, it's random because we are sampling from a random latent feature vector at the left-hand side of the GAN. So if you change the random feature vector, it will generate a different image, but still it will have those properties that here's a car. If you change the random feature vector, you might generate a red car or a Porsche, but actually it will generate a car position because the semantic map is taken as input. You can create images from text. Here, this flower has long, thin yellow petals and a lot of yellow anthers in the center, and the GAN is generating those images. Image in painting. You remove a part of the image and the GAN paints the rest of it for you. Because it has seen, I don't know, 1 million images of birds and children and boats, it's somehow, like a human, somehow knows what to fill in. And I think it's outperforming humans, by the way. To me it seems a human couldn't do that. Music generation, that's the only non-image example which I've found. So you can train it with MIDI data and it will generate new MIDI data for you. Also based on the latent feature vector, it generates random but relatively nice sounding music for you. And this slide is empty because that's the thing I'm currently working on. I will create a better anomaly detector. So my current anomaly detector, which I've developed, is based on the LSTM and autoencoder, which is already pretty nice. But now the next one I will try out the GAN. So the GAN will be trained on our time series data, which we get from the sensors, and it will recreate time series data, and I will compare those time series. If they are matching, we don't have an anomaly, and if the real data doesn't match to the generated data, I think we have an anomaly, because the neural network has now learned how normal data looks like, and if that data which it generates doesn't match with the real data, we have an anomaly. So that's the. So next time I come back to Munich, this slide will be won't be white. Yeah, just one little promotional slide before I show you the demo. Please consider taking my Coursera courses, and I will post the link into the meetup group. We will have a couple of 10,000 free tickets for the Coursera course, because my manager managed it, and you will learn how to do it. You might have to help Ralph with the challenge to get the free voucher, but anyway. So you have the 4 courses. The first one is Fundamentals of Scalable Data Science. So I'm a big fan of Apache Spark, because always if I do machine learning without Spark, it crashes, because it's an out-of-memory exception if I use scikit-learn or R. Therefore I'm a big fan of Spark. You don't have the problem there. Second, advanced machine learning means scalable machine learning using Spark ML, but in addition, most of our data is time series, and we often just ignore the time aspect of it. Therefore, learn some signal processing as well. So wavenets and tsfresh and FFT and so on, also on Spark. And then, of course, the whole deep learning topic. So I've taken a couple of slides from week number 1, which gives you the introduction. Week number 2 is about frameworks, TensorFlow, Keras, PyTorch, SystemML, and deep learning for J. Week 3 is about applications, anomaly detection, time series forecasting, image classification. I will add the GAN stuff in there as well once it runs. And the last one is the capstone, where you have to solve a challenge end to end, and then you get basically a certificate from IBM and Coursera. So that's all about this. And now let's have a look how my GAN works. So this is here running a Jupyter notebook. So I had to upgrade to the latest TensorFlow version, and then, so it's a TensorFlow sample. I'm not very happy about that, because I hate TensorFlow. It's too complicated for me. I'm not intelligent enough for TensorFlow. Therefore I use Keras. It's much more straightforward, because you're only working on layers and not on matrices. So anyway, it's a bit hard to understand, but actually what it does, it creates here a generator network. You see here some leaky ReLU as activation function applied. You see here some upsample layers. That's the one which are actually adding dimensionality to your proposed image. And you have the discriminator, which is a more or less ordinary convnet. You see here the leaky ReLU activation function, also the convolutional layers. Yeah, it's not that bad. It could be worse, because they are at least using the API on the layer level. But Keras is still better. Okay, I will find a working Keras solution for you soon. We have the noise function here for creating the latent input vector. We have some visualization. And then, interesting part here is the training. So the cool thing is here, every 100 iterations, it will update this matrix here, which contains the generated images. So for those who know the MNIST dataset, those are 60,000 labeled training handwritten digits. And here, after 11,100 iterations of training, that's the performance of the generative model. So all those numbers are now created by the generative model, which is quite cool. So I just have to plug in my CryptoKitties. Of course, I have to change it, because it's a 3-channel problem, because it's a color image. This is a monochrome, but anyway, I will be able to do that. Then you see here, it will take another 40 hours to complete.
Well, what's happening? What are you doing right now?
So I'm training. So I'm running the optimization objective with a joint optimization objective between the generator and the discriminator on the 60,000 MNIST images on 4 cores and 60 GB RAM. That's unfortunately the biggest free runtime you get on Watson Studio. Otherwise you have to pay. But I thought I'd just let it run.